All right, welcome to The Explainer. Today we are going to crack the code on what is, without a doubt, one of the most powerful languages in the modern world, statistics.
We're bombarded with data every single day, right? It's in the news, it's in studies, numbers are just everywhere. So the big question is, how do we actually make sense of it all? Well, let's dive into the one essential tool that lets us separate the real story, the signal, from all that noise.
And yeah, you guessed it, that tool is statistics. But look, it's not just about crunching numbers. It's really this formal framework for making sense of complex information. I like to think of it as our map and our compass for navigating this crazy world of data. It helps us find those meaningful insights and, make decisions that are actually informed.
Okay, so here's our game plan. First, we'll nail down the fundamentals. Then, we'll jump into the two main branches of stats. After that, we'll see how you can use a small group to understand a massive one, check out the tools we need for today's big data, and we're going to wrap up with something super important, ethics. Let's do this.
All right, first up, making sense of data. Before we really get into the weeds, we got to be on the same page. We need a clear definition of what we're even talking about when we say the word statistics.
So, it's a systematic science, right? It's the framework that lets a company say, look at all its customer feedback and actually improve a product. Or it lets a scientist figure out if a new drug really works. It gives us that structure to go beyond just a pile of numbers and pull out real, actual knowledge you can use.
Okay, so you can pretty much split the entire field of statistics right down the middle. There are two main paths, and each one is designed to answer a totally different kind of question. Basically, it comes down to this. Are we just describing what we can see right in front of us, or are we trying to predict something we can't see? And this is that fork in the road, right here. On one side, you've got descriptive stats. That's all about the facts. What does the data you have actually say? It's like drawing a perfect blueprint of a house you're standing in. On the other side, we're making an educated guess. We're using a little bit of data to predict something way bigger, something we can't measure directly. Think of an astronomer using a small patch of sky to understand the whole galaxy.
So, let's stick with descriptive statistics for a second. It's all about creating a super clear, high-res snapshot of your data. The whole point is just to summarize what you've got, plain and simple. No guessing, no predictions, just the facts. And to paint that picture, we use some key measures, like what's the center of the data? That's your mean or median. How spread out is everything? Are all the numbers clumped together, or are they all over the map? That's where standard deviation comes in. We can even look at the overall shape. Is it a nice, neat bell curve, or is it kind of lopsided? It's basically a full diagnostic report on your data.
Okay, now this is where things get really, really powerful. Inferential statistics. This is where we make a calculated leap. It's not a blind leap of faith. It's about taking a small, manageable piece of evidence, what we call a sample, and using it to understand the much, much bigger picture, the whole population.
And to make that leap responsibly, we've got a whole toolkit. We use things like hypothesis testing to see if our ideas actually hold up against the data. We use confidence intervals to say, okay, here's our conclusion, and here's how sure we are about it. This is what lets us make those big, broad conclusions, but with a degree of confidence we can actually calculate.
So let's zoom in on that idea for a second, moving from a small group to a big one. Because this leap from the sample to the population, honestly, it's the engine that drives all of inferential statistics.
Okay, I love this analogy. The population, that's the entire pot of soup you just made, the whole thing. The sample, that's the one spoonful you taste to see if it needs more salt. Now here's the key. That spoonful has to have a little bit of everything in it, right? The carrots, the broth, the noodles. It has to be representative. If it is, your conclusion about that one spoonful is probably true for the whole pot.
And the big takeaway here is that this isn't just a wild guess. It is a strict, rigorous process. You have to follow the steps. First, you define exactly who you're talking about. Then, you draw a really good representative sample. You analyze that sample inside and out. And only then can you generalize what you found back to the bigger group.
Okay, so we've been talking about samples and populations, which is great. But what happens when the population isn't a pot of soup, but an entire ocean of data that's being created every single second? Yeah, let's talk about how these classic ideas are getting supercharged for the world of big data.
You've probably heard the term big data, and it's defined by what people call the 3 V's. First is volume. We're talking a massive, massive scale. Think every tweet ever tweeted. Then there's velocity. It's coming at you at incredible speed, like data from the stock market. And finally, variety. It's not just numbers anymore. It's text, images, videos, sensor data from your watch, you name it. Your standard old software, it just can't handle this stuff.
So how do we deal with all that complexity? Well, one of the key tools is something called regression analysis. It's a way to look at the impact of a whole bunch of different things all at once. This is super important for avoiding something called confounding. That's when you think, oh, A is causing B, but really, there's this hidden factor C that's causing both of them. Regression helps us untangle that whole messy web.
And to actually crunch all those numbers, statisticians have come up with some really clever strategies. There's divide and conquer, which is exactly what it sounds like. You take a giant problem, break it into smaller, manageable chunks, and have computers work on them all at once. Then there's online updating. This is perfect for streaming data because it just keeps updating the analysis as new info flows in, without having to save every single piece of data from the beginning.
But you know, all of this power, the power to analyze, to predict, it comes with a huge responsibility. And that brings us to what is, I think, the most important part of this whole conversation, the ethics of doing statistics.
This quote here from the American Statistical Association really nails it. The end goal isn't just to get an answer or publish a paper. The whole point is to serve society, to provide judgments that are sound, that are responsible, and that are truly informed.
And these ethical guidelines are built on some core principles. It's about being totally transparent with your method so people can check your work. It's about protecting the privacy of the actual human beings behind the data points, and it's about being accountable for the impact of your analysis. These aren't just, nice suggestions. This is the bedrock of trustworthy science.
And this is such a critical point. At the end of the day, statistics is a human thing, and it has real-world consequences. A good ethical statistician is always thinking about the potential impact of their work. They're actively trying to avoid causing harm or making existing inequalities even worse.
So look, as we've seen, statistics is this incredible toolkit for finding the truth that's hiding in data. But the numbers themselves, they're neutral. The methods give us insight, for sure, but the choice of how to use that insight, how to wield that power, that's on us. So the real question it leaves us with is, how are we going to make sure this powerful tool is used for good?